Hi everyone, this is Dominique from FEA Academy. Today we are going to talk about introduction to modal analysis by FEA for this episode of FEA Insight. Here is the agenda of this presentation. I'm going to start with an introduction to modal analysis, obviously, and then I want to talk about the eigen equation to present you what is the eigen equation and the numerical methods for solving the eigen equation. Then I'm going to answer the question what a mode is and what a mode is not, and how our natural frequencies influence. Then I'm going to show you how to compute a modal analysis and share with you few examples of modal analysis, because you will see modal analysis can be used in many occasions. So let's start with an introduction to modal analysis. Modal analysis is the study of the dynamic properties of linear structures using finite element analysis simulation. These dynamic properties include natural frequencies and structural modes. These properties are dependent on the mass and the stiffness of the structure that you want to analyze by modal analysis, and define structural vibration behavior when exposed to operational loads. Model-based calculations are very effective and allow efficient evaluation of structural changes. So let's start with the eigen equation. What is exactly? I want to start first with the general equation, the general equilibrium equation, I should say, that you have on the screen. You recognize the different parameters of this general equilibrium equation. The mass matrix, the damping matrix, the stiffness matrix, and also the excitation vector, I should say. And then you have the different variables, the displacement vector, the velocity vector, and the acceleration vector. So this general equilibrium equation shows how they are related to each other. When we want to solve this general equilibrium equation, we can do different assumptions, and depending on the assumptions we do, we obtain a different problem to solve. And the vibration analysis is this, we obtain this equation, okay, which is the equation of modal analysis. So the eigen equation typically is the equation we want to solve. How do we derive this eigen equation? So everything is starting from the for sure the equilibrium equation of continuum solid mechanics that you know now. And we do an assumption. We do the assumption of the equation of motion for undamped free vibration. It means that we neglect the damping of the system. So we obtain this equation, okay, where we have the mass, the acceleration, the stiffness, and the and the displacement. Now we have to make an assumption, the assumption on the solution. We assume an harmonic solution, and obviously when we assume an harmonic solution, it is the equation here that we obtain. So by doing two derivations of this equation and put that in the equation of motion for the undamped free vibration, we obtain the eigen equation that you have here on the screen, where lambda equal the square of omega, which is the eigenvalue, and the natural frequency, which is omega divided by 2 times pi. Here, typically, this vector, it is what we call the associated eigenvector with the natural frequency, or the mode shape. So at the end, the name we give at this type of analysis, it is the real eigenvalue analysis, or the normal mode analysis. You can use both of the term when you talk about this kind of analysis. So let's have a look at now the numerical methods we are using in order to solve the eigen equation. The two most popular methods that we are using in various industries, and there are other methods, okay? But here are the two most popular methods used in the industry. The first one, it is the enhanced inverse power method. The second one, it is the long sauce method. Okay. The influencing factors on the performance of the computation are the total number of degrees of freedom of the problem. Obviously, the more degrees of freedom you have, and the longer it is to compute the equations. The number of computed eigenvalues. If you want to compute only the first natural frequency / eigenvalue, it takes less time than if you want to compute the 100 or 300 first eigenvalues. It depends also on the available computer memory, obviously, but also how well you can estimate the range of eigenvalues for a given problem. So, as I told you, here are the two most used methods to solve the eigen equations. So the enhanced inverse power method is good only if few modes are needed, okay? In the sense that if you need less than 50 modes or less than 30 modes, few modes, it's very good, okay? And it's good also if you have a reasonable idea of your eigenvalue range, because you will have to provide to the solver the range of eigenvalue you want to extract from the system. On the other hand, the long sauce method is more efficient for a large number of modes. And the huge advantage of the long sauce method is the fact that you don't need an initial estimate of the eigenvalues. And it is the reason why the long sauce method is used most often for the industrial problems. So let's answer this question. What a mode is and what a mode is not. But let's start with the natural frequency. An object's natural frequency is the frequency at which it vibrates naturally when disturbed. So what is the mode? The mode, it is the deformed shape, okay, plus the natural frequency at which the mode shape occurs. So if we deform a structure into any of its mode shape and we release it, it oscillates continuously at the natural frequency of the mode in question. So a mode is a shape with a corresponding natural frequency at which the structure will absorb all the available energy provided by an excitation. So if we deform a structure into any of its mode shapes and release it, it oscillates continuously at the natural frequency of the mode in question, okay? So in the undeformed state, at this stage, there are two interested states, okay? The undeformed state and the maximum deformed state. If we start with the undeformed state, the velocity at every point is at its maximum, okay? So the kinetic energy is maximum at the undeformed state, while the potential energy is 0. On the other hand, at the maximum deformed state, the instantaneous velocity is 0. So it means the kinetic energy is 0 and the potential energy is maximum. So it means that the mode shapes have nothing to do with the magnitude of displacement of the system. So how are natural frequencies, and mode shapes influence in the system? For a given structure, the natural frequencies and the mode shapes are function of the structural properties and the boundary conditions. Here you have the equation, the typical equation for the fundamental frequency. Okay, so you see that the two parameters here are the stiffness and the mass. The stiffness K and the mass M of the structure, both given by the geometry and the material properties, influence the structure's natural frequencies and the mode shapes. If the Young modulus, for example, of a structure is changed, so the stiffness is changed, the natural frequency will change, while the mode shape could remain unchanged. If the stiffness of the structure increases, you see from this equation that the natural frequencies increase. On the other hand, if the mass m of the structure increases, the natural frequencies decrease. Okay, so you see this relation between frequency, K stiffness, and M mass is very important to understand, because it explains you how you will influence the natural frequency of the system that you are designing. If the boundary conditions, by boundary conditions here, I'm talking about the restraints, okay, of the structure. If they are modified, both the natural frequencies and the mode shapes will change. So why do we want to compute a modal analysis? First, modal analysis can provide very useful information in various situations. The first one is defining the natural frequencies at which a structure tends to vibrate and the associated mode shapes to avoid resonance. You know that resonance can destroy a structure, literally. So the modal analysis permits you to calculate the natural frequencies in order to avoid the resonance. The second application of doing modal analysis is identifying possible modeling mistakes. For example, the missing connections between components or constraints incorrectly defined. You can use a modal analysis in order to do that. I'm going to illustrate that later. Finally, modal analysis is used to define the behavior of the system under dynamic loading. It is the third application of modal analysis. So let's see few examples of modal analysis to illustrate the three categories I presented before. And let's start with using modal analysis to avoid resonance. Avoiding resonance is what it is. Avoid resonance. It is an assessment about the interaction of a component with its surrounding structure and environment. A typical example is a wing's natural frequencies close to the operating frequency of the rotating engine fan. You know, the rotating engine fan is creating a certain excitation at a certain frequency depending on the RPM of the engine. If this excitation frequency is synchronized with the natural frequency of the wing will be destroyed by this excitation. So this operating frequency of the rotating engine fan needs to be completely dephased compared to the natural frequency of the wing in order to avoid the destruction of the wing. Another example, it is the stability of a bridge under a cyclic wind effect. You see on this video, the bridge is completely destroyed just by the wind. The reason why is because the wind effect here on the bridge occurs at a certain frequency. And here on the video, the frequency is match exactly the natural frequency of the bridge. And you see nobody on the bridge. There is no excitation from cars, from a track, nothing, just the wind. and you see the bridge is completely destroyed. So it's a typical example of resonance. So you see, it's a very important assessment because resonance can lead to catastrophic failure. So I'm going to show you here a first example, but it's a very simple example, which is a stiffness panel. Imagine you need to build this stiffness panel and you need to install into a system, a mechanical system, close to a rotating system. And this rotating system is running at 130 Hertz. So you need to avoid resonance with the rotating system at 130 Hertz. And you want to keep a 10% margin, okay? At the beginning, you are allowed to design the stiffness panel using aluminum and steel materials. It's up to you. But you have a constraint. The constraint, it is a maximum weight of 4 pounds. So you have the choice. You can build several configurations of the stiffness panel and test it with the excitation at 130 Hertz and verify if the panel is destroyed by the excitation. It will cost you a lot of money because you will have to build many panels with corresponding to the different configurations. Or you can do numerical simulations using normal mode solvers and compute the natural frequencies of your panel by varying the material, the construction, the configuration of the stiffeners in order to find the configurations which give you the right solution. Let's have a look at that. First, I want to show you how you need to model the panel. Here, it is a stiffness panel, a typical stiffness panel where you have in blue the panel itself and in red the stiffeners at a certain pitch with a certain dimension of stiffeners. So the question is, what is the thickness of the plate? What is the height of the stiffeners? What is the pitch of the stiffeners? I have to build in order to have a panel satisfying the requirement. So what I'm doing a model using 2D shell element. So you see it's a full 2D quad model. And I represent the panel in blue, the stiffeners also with the quad element. And I connect the stiffeners with 1D spring element at the exact location of the fasteners with the proper stiffnesses for the 1D spring element calculated using the HUT formulation. Okay? So I have a model representative in stiffness and representative in mass, because in the material properties of this panel, I'm going to use steel or aluminum on different simulations, and I'm going to inform the solver with the material density. So the solver will be able to compute the stiffness matrix and the mass matrix of my panel. Okay? So remember, in the equation of natural frequency, the two parameters which influence the natural frequencies are the stiffness and the mass. It is the reason why your model needs to be extremely accurate in stiffness and in mass. It is the reason why I'm modeling in detail the panel, the stiffeners, the fasteners in my model. So here are the 5 configurations that I'm going to simulate. So here you see 5 configurations, but I don't build even one configuration. Everything is numerical. Okay? I vary the plate thickness, the plate material between aluminum and steel. I vary the stiffener thickness and the stiffener material between aluminum and steel. So you see here on the last column the different weight I obtain for each configuration. So without building any model, any panel, just by doing only model, I already know the models which are above the 4 points that the requirement is giving to me. That's very good. Here you have the material properties for aluminum and steel with Young modulus, Poisson ratios, and the density of materials. It's in imperial units, but you can replicate this example also in the international system, for sure. And so here are all the parameters that material and geometric that I am using to build the model and to test with a normal mode solver. Here I am using the Nastran solver, but all the commercial FEA solver can do this analysis, the normal mode analysis, in order to compute the natural frequencies with the associated mode shapes. So here are the results I obtained. You see, for the 5 configurations. A very important information here, it is the first mode, okay? So keep in mind that the requirement is I need to be above 130 Hertz with 10% margin in order to avoid resonance, okay? So you see the configuration 3, it's a very good candidate because the first natural frequency is 146.8 Hertz, which is above the 10% margin. But the problem is the weight. It's 4.6. The requirement says 4. Let's have a look at the configuration 4, because the configuration 4, the weight is good, it's 3.5 points. But the first mode is 138.7 Hertz. And I am above 130 Hertz, but it's less than the 10% margin that I need. So it's not a good candidate. Finally, the configuration 5, it's less than 4 points, and the first mode is 143 Hertz. It's above the 10% margin of safety. Okay, so it is the lighter solution with a good margin. So it is a good candidate. For sure, the first one is very light, but you see I am below 130. And the second one also is below 130. This one is interesting, you see, because it is the same plate thickness. I changed only the material, okay? It is also the same stiffener thickness and the same stiffener material, but only the plate stiffness change. It's from aluminum to steel. So since the plate material is a steel, it is a stiffer, but also it is heavier because it is steel. So K over M, it means M increase because I increase the density by switching to steel. So I increase the mass, so I decrease the first natural frequency. Even if I increase the stiffness by going from aluminum to steel, but the mass kills the system. Here are animations showing the 3 first modes for the solution, the configuration 5. Okay, it is also the advantage of modal analysis. You can animate the normal mode, the eigen vectors associated with each natural frequency. Now let's see a second example based on avoid the resonance. It is the communication tower example. The Aeolian vibration are caused by low velocity steady winds. And normally those winds, they range from 5 to 35 mph, so between 8 to 58 km per hour. Okay, and these winds are typically they give frequencies in the range of 2 to 20 Hertz. Here I am talking about the excitation frequencies. Okay, where does it come from? It comes from a vortex effect. So you see on the picture here, you have the tower. So we see the tower from the top. Okay, and you have the wind, the transverse wind here like that, and here the tower creates a separation of the wind. Here behind the tower there is a vortex effect, and this vortex effect create side loads, and those side loads, they oscillate a lot. They oscillate between 2 and 20 Hertz. So it creates an excitation on the tower. So this vibration can destroy the structure in few minutes in case of resonance. It is what you see here on the picture. Typically, this tower has not been analyzed in natural frequency, and it is completely destroyed. So I decided to do a numerical simulation of this tower. Okay. So the geometry is this one. It's a tower in steel. The height is 25 meters, 83 feet, and it is made of I-beams. So the FEM has been built using 1D beam elements and lumped mass. Why lumped mass? Because keep in mind, we have to capture properly the stiffness, but also the mass of the system, here of the tower. The mass of the tower, it is not only the mass of the structure, it is also the discrete mass of the antenna attached on the tower. And those masses are not negligible. So I modeled the masses of the antenna with a lumped mass. So what is the objective here? The objective is to make sure that the communication tower has no natural frequencies in the range of 2 to 20 Hertz. 2 to 20 Hertz, it is the frequency of the excitation due to the vortex, the wind vortex. Okay. So here it is a picture of the model. You see, you see the cross section, the I-beam. So you have two categories of beam: the strong beam vertically, plus a lighter beam here to close the tower. But it's a typical configuration for this kind of communication tower. Okay. And here you see the lump mass, different lump mass attached using MPC elements to the tower, as I told you, because the total mass of the system is really important to capture properly. So the mass of those antennas here are properly captured. Here it is another picture showing details of the model. So you see everything is in 1D beam. Here you have a 3D representation to show the cross sections. Okay. And here on the picture of the real tower, you see the different antennas. So here the antennas are attached, or represent, I should say, not the stiffness of the antenna, because the stiffness of the antenna has no influence. What is important, it is the stiffness of the tower, but the mass of the antenna is very important. And also the boundary conditions. So typically here we know that the tower is firmly grounded, okay, on the ground. So the tower is restrained at the base in the translation and rotational degrees of freedom. So let's have a look at the results. So I ran a normal mode analysis using my solver, and then I import the results into the post-processing software, and I create animations of the different natural frequencies with the associated mode shape. So here it is the first mode at 2 Hertz, 2.44 Hertz, and it's a bending mode of first order. You see, it's the very basic. I predicted this mode as the first mode, but not the stiffness, not the frequency. So you see, it's exactly in the frequency of the excitation between 2 and 20. So here with the first mode, I have a resonance, and it is a global mode. The second mode, it's a second order mode, and it is still a bending mode at 2.40 Hertz. The third one, it is a 12.7 Hertz. It's also another bending mode second order. Even the fourth mode, a bending mode. And here I have a torsional mode. It is the mode 5, but you see still in resonance, 14.5 Hertz, still in the range of the excitation. That one is very interesting. Now it's a local mode. It's not a global mode. You see it only the beams at the base of the tower. But it will destroy the tower because it's exactly in the excitation range, 16.7. Just to show you that normal mode analysis is very powerful, because if your model is very accurate, you can capture the global mode, but also the local modes. Another local mode, close to 20 Hertz. And now you have this mode, which is a combination of a global effect, a global mode and local mode. Because you see there is a global bending and here some local effects. But that one is 32.6, so it's out of the range of excitation. So you see, with a very simple model, I validated the fact that my tower, without building any tower, I validated the fact that my tower will be destroyed by a wind. Okay? So, sorry, if I come back here, you see, if I go back to the first one, the first mode I want to solve, I need to solve the bending mode. So I have many choices. I can increase the base of the tower to solve this problem, or I can even use some reinforcement going like that and like that in order to stabilize those modes. And then I can implement that into the model and rerun the numerical simulation to see how the natural frequencies are shift, okay, in order to go outside of this critical range, the vortex wind range, with a certain margin of safety, let's say 10 to 20% of margin of safety. So now let me illustrate you how to use model analysis in order to find mistakes in the model. So here the objective of the model analysis is really to validate, no, not to validate, to verify errors into your model. Okay? So a free, by free I mean without boundary condition, a free model analysis check permits to verify that the model will act as rigid body when it is unconstrained. So it validates that only 6 rigid body modes exist to the model in the free condition. On top of that, the flexible modes allow for the isolation of weak or very flexible regions of the model that may be due to a modeling error or an unwanted internal boundaries or even disconnected parts. So let me illustrating you this kind of verification using again another simple example. And here I come back to the stiffness panel that we discussed before. It is exactly the same stiffness panel, but this time we are going to use a model analysis, a free model analysis, to verify that the model is correct. Okay, so the panel and the stiffeners are modeled with 2D shell elements. They are connected together using 1D spring elements having the proper stiffness in shear and axial stiffness using the HUD formulation. Now, as I said, let's run a free model analysis to check at the connectivities. For that, what we're going to do, we're going to remove all the external constraints, usually the single point constraint or SPCs, okay, which usually restrain a model in order to remove all the rigid body motion. In that case, we remove them. We set up a standard normal mode analysis, and we recover 25 modes using the Lang-Sauce method to compute the associated eigenvalues and the mode shapes. So to show you the powerful of the solution, I generated 3 scenarios. The first scenario, it is when the stiffeners are properly connected. By that I mean all the stiffeners are connected to the panel with 1D spring element at each fastener location with the proper stiffness in shear and axial. This is the first scenario. The second scenario, it is with a stiffener locally disconnected. So you see here in this circle, when I created the model, I forgot to create the 1D spring elements representing the fasteners attaching the stiffener to the panel. You know, it can be a typical error that we are doing when we build a model with a lot of fasteners. Maybe you can forget to create those fasteners, okay? But you don't see it because the 1D spring element are only small lines, okay? 1D element between 2 nodes. So visually speaking, when you check the model, you don't see it, okay? The third scenario, it is the same panel, okay? But in this case, all the stiffeners are properly attached with the 1D spring elements, but I made a mistake when I defined the stiffnesses of the 1D spring elements. I forgot to define the stiffness in shear, okay? I defined only the stiffness in the actual direction of the 1D spring elements. So here are the 3 scenarios, and I run them using the same solver, the same solution, a normal mode analysis. We call that the free modal analysis in the sense that we don't apply any boundary conditions. So what do we expect? We expect 6 rigid body modes. By that, it means that we expect 6 modes with very low natural frequencies, usually less than 1e minus 4 Hertz. And after that, we expect the flexible modes with significant natural frequencies. Okay? So let's have a look at the results. Here are the results I obtained with the 3 scenarios. So you see scenario 1 and scenario 2. So I remind you, scenario 1, it is the stiffeners properly connected. The scenario 2, it is the stiffened panel, but with a stiffener locally disconnected without any 1D spring elements. So I can see my rigid body modes, I have 6. The frequency correspond to rigid body modes, very low frequencies. And after that, I have my flexible modes. And from a physical point of view, those natural frequencies, they make sense, okay? Because the first mode, 17.3 Hertz, after 24.4, 43, it makes sense in physically speaking. So just looking at the table of the natural frequencies, I say, oh, my model is okay, I check, validated. But it's not the case. I will come back on that later. Now let's have a look at the natural frequencies for the scenario 3, where I implement the wrong 1D spring stiffness in shear. You see, I have only rigid body, rigid modes. Very low frequencies. The first mode, 1.6, or let's say 1.7 E minus 3, and mode 25, 1.7 E minus 3 Hertz. All those modes are rigid modes. So just by watching at the list of modes, of natural frequencies, sorry, I know that this model has a problem. And for those 2 models, I suspect they are correct, but it's not the case because, as you know, this one is correct, but this one is not correct. What can I do in order to identify which one is correct? It's very simple. You have to watch at the mode shapes associated with each natural frequency. It is what we are going to do in the next slide. So you see here, we are with our post-processing software, we are doing a deformation plot with animation, but here it's not animated, it's just deformation plot, of the rigid modes for the scenario 1 and 2. And you see, we validate, visually speaking, that we have rigid modes because the complete panel is moving, the stiffeners with the panel are moving together, okay, at a rigid mode. So it validates that everything is correct with scenario 1 and 2 by looking at the rigid mode. Again, here still mode 3, mode 4, mode 5, mode 6. Rigid mode, perfect. If I look only that, I say the model scenario 1 and the model scenario 2 are correct. I have no problem. But it's not the case. You have to continue the investigation. You don't have to look only at the rigid mode. You have to look at the flexible mode from the mode 7. Let's do it. So here we are looking at the scenario 1, which is the scenario where the stiffeners are properly connected. The flexible mode 7 and the flexible mode 8, here it informs you that everything is working together in the flexible mode. And it is what you expect, because what you want to model is a stiffened panel having stiffeners properly attached to the panel. Okay? So everything is perfect. And even in the high mode, you see the high order mode, I should say, everything is moving together, the stiffeners with the panel. So it's a very good validation for the scenario 1. Rigid modes and flexible modes, it is what I expect in terms of continuity of the mode shape. Now let's have a look at the scenario 2 for the flexible mode. And here I did an animation because it's easier to capture the problem. So you see the first flexible mode, which is the mode 7 at 17.1 Hertz, and which is the model with the stiffener locally disconnected. I see this stiffener is not working with the panel. It's easier to see that in the next mode, the mode 9. You see, the stiffener is going through the panel. It shows me that clearly this stiffener is not attached with the panel. Otherwise I would not see this stiffener going through the panel. We see that on the mode 10 also. You see, in the mode 10, this guy is working together, not together, alone, sorry. You see, it's clearly obvious that this stiffener is not attached to the panel just by looking at the mode shape associated with the natural frequency. But you see the mode 12, if I come back to the table, it's very scary because if I look only at the table, you see the stiffener, the natural frequency, they are close. You see 67.1, 67.0, 85.4, 85.9. So looking just at the natural frequencies, it seems that everything is correct. So it shows you that you absolutely need to plot with your post-processing software at the mode shapes associated with the natural frequencies in order to capture this kind of problem. But you see the powerful of the solution. So now let's have a look at the scenario 4. The scenario 3, when the stiffeners are properly attached to the panel with 1D spring element at each fastener location, but with the wrong stiffness. In that case, I remind you, I forgot to specify the shear stiffness. I only specified the actual stiffness. Look at the first rigid mode. Even the rigid mode is not a rigid mode, because if it's a rigid mode, everybody is working as a rigid body. Here it is not the case. This stiffener is moving alone. This stiffener also, it is the flexible mode 10, is moving alone. But the mode 10 should be a flexible mode, not a rigid mode. Okay? So you see the powerful of the normal mode analysis to validate a model just by computing the natural frequencies and the eigenvalue, eigenvectors, or the mode shapes associated with each natural frequencies. So keep that in mind. Don't look only at the table of frequencies. Plot also and animate the mode shapes associated with each natural frequencies. The last usage of modal analysis I want to show you here is use modal analysis to understand the dynamic response of a structure. Here, by understanding the dynamic response of the structure, I mean predict the contribution of the modes to the total dynamic response. We call that the modal effective mass. It characterizes the relative contribution of the modes when the structure is excited along a direction with a given frequency. So it is like a method for judging the significance of a vibration mode. Here you see on the right some animations, some modes for a building. Okay, so modes with relatively high effective masses can be easily excited by base excitations, and modes with low effective masses cannot be easily excited in this manner. So it's very important before to conduct a dynamic analysis to have the knowledge of that. Okay, how the mass will influence the response. So here it is this graph, it is a very simple illustration. It is from Chris Hall from Value Design Consulting. So you see, you have a beam, we can say a cantilever beam, with three modes. The first mode, which is the first order, the mode 2, second order, the mode 3, third order. That one, it is a higher mass participation, and this one, it is a low mass participation. So this mode, it's a lower frequency, but you have more mass participating into the mode. It is obvious. You see more mass here moving with moving in the mode shape. And here it is higher frequency, but you have low mass involved in the excitation. So it means that the modal effective mass computation provides the total effective mass in each direction. So it permits to determine the number of modes that should be included in a modal transient or a frequency response analysis. And why it is important? It is because the total effective mass of the model in each direction should be at least 80% of the actual mass of the system that you are going to analyze. Okay, so when you do the simple normal mode analysis, you can ask the solver to compute for you the total effective mass, and you obtain this kind of table. Here in this example, I run a simulation and I ask the solver the modal mass fraction, okay, that I ran using a normal mode solver. And I extracted 25 modes using the long source method. And I built this table. The total effective mass of the model in each direction should be at least 90% of the actual mass. So if I want to use this mode to run a dynamic frequency response analysis of this structure, this table inform me that I need to compute more than 25 modes. Because you see here in translation X, Y, I capture 99.6% of the total mass with only 18 modes. But with 25 modes, I'm not able to capture at least 90% of the total mass in the translation Z degree of freedom. And it is the same in rotation X and rotation Z. And it is even worse because in rotation Y, it's only 78.6% of the mass. So 25 modes, it's not enough. I need to go further, probably 50 modes or maybe 100 modes. To know that, I need to run the normal mode analysis to make sure that when I'm going to run my dynamic frequency response analysis, I will have enough modes for my linear superposition in order to capture the right frequency, dynamic frequency response of the system. So you see the basic normal mode analysis gives me very important information about the dynamic nature of the problem. So that's it for this presentation. Again, if you want to know more about normal mode analysis and other examples, you can see the book Practical Finite Element Analysis for Mechanical Engineers, available on the FEA Academy website. And also, you can go through the online on-demand FEA Academy courses, Practical Basic Finite Element Analysis or Practical Nonlinear Finite Element Analysis, to go further in your knowledge of finite element analysis. This is Dominique Maguier from FEA Academy. See you in the next episode of FEA Insight.